Welcome to the Late Lab. It's a pleasure to have you here. Before settling in, it would be lovely to imagine where this finds you tonight. Perhaps the room is dark and quiet at the end of a long day. Perhaps the world outside has finally gone still. Wherever you happen to be listening from, the hope is that you are warm, at ease, and ready to let your thoughts wander gently for a little while. If these slow explorations into science help make the evening a little calmer, then a like and subscribe really do help this small channel keep going. And for those already subscribed, thank you. Your support is deeply appreciated, and it helps keep these quiet little journeys possible. Now, tonight's subject may not be the most sensible thing to drift off to, because quantum physics has a habit of making the universe seem far stranger than it has any right to be. Still, there are worse problems to have in the middle of the night than quietly wondering why light behaves like a wave matter, behaves like a probability, and the foundations of reality seem just a little less solid than they look. So, let the day fall away for a while, and let's ease into it together. Because at the smallest scales of existence, the world stops behaving like common sense and starts behaving like something much deeper, much stranger, and much harder to ignore. Ordinary life does not usually feel mysterious. A floor feels solid beneath your feet. A glass of water looks clear and calm. Sunlight spills across a wall as if it has done the same sensible thing every morning forever. Skin, wood, stone, air, metal, breath, warmth, colour, all of it seems steady, familiar, and entirely uninterested in causing philosophical distress. Most of the time, reality appears to behave like a well-trained employee. It shows up, does its job, and avoids making a scene. And yet that surface of normality rests on something far stranger than it appears. Beneath every visible object lies a world that does not behave in the way common sense expects. The familiar world is made of atoms, and atoms are made of smaller ingredients still, including electrons, protons, and neutrons. Go deeper than that, and the picture becomes stranger again, because the smallest scales of nature are governed not by the neat, predictable rules of classical physics, but by quantum mechanics. That is the framework developed in the early 20th century to describe matter, light, and energy at very small scales, where certainty begins to loosen its grip. This is the quiet surprise at the heart of everyday reality. The world that feels stable and obvious was not simply decorated by quantum physics as an afterthought. It was built from it. Every solid surface, every chemical bond, every shaft of light, every living cell, every screen, every breath of air depends on rules that are, at first encounter, deeply unintuitive. Classical intuition suggests that objects should have definite positions and definite paths. Thrown stone travels from one place to another. A planet orbits a star. A pendulum swings. This older picture of physics, shaped by Isaac Newton and later refined by generations of scientists, is extraordinarily good at describing the motion of large things. It can explain falling apples, orbiting moons, moving trains, and crashing waves with remarkable precision. For centuries it gave the impression that nature at its core was orderly in a very mechanical sense. If one knew where everything was and how fast it was moving, then in principle the future could be calculated. That picture works beautifully for many things, but it begins to fail when the world is examined at atomic scales. There, light does not behave purely like a wave, and matter does not behave purely like a little pellet. Electrons do not orbit in the tidy planetary way that old illustrations once suggested. Particles can only occupy certain energy levels. Outcomes are described in terms of probabilities rather than certainties. The deeper the investigation went, the more it became clear that the foundations of ordinary reality were nothing like the reality of ordinary experience. This shift did not happen because scientists became bored and decided to make things more complicated for sport. It happened because experiments forced the issue. At the end of the 19th century and the beginning of the 20th, several problems began to appear in physics that classical ideas could not solve. One of the most important involved blackbody radiation, which is the pattern of light emitted by an object because of its temperature. Classical theory predicted the wrong result, and not by a charmingly small amount. It predicted a catastrophe. In 1900, Max Planck found a way through by proposing that energy is emitted in discrete packets, later called quanta. He did not set out to destroy the older picture of reality, but he quietly opened the first crack. A few years later, Albert Einstein pushed the matter further by explaining the photoelectric effect, in which light striking a metal surface can eject electrons. Classical wave theory alone could not explain the observed results. Einstein proposed that light itself behaves as if it comes in packets of energy, now known as photons. This was an extraordinary suggestion, because light had long been understood as a wave. Suddenly it seemed that nature had no obligation to fit neatly into the categories humans found comfortable. Then came Niels Bohr, who developed an early quantum model of the atom, showing that electrons in atoms occupy specific allowed energy states. Werner Heisenberg later helped establish matrix mechanics and formulated the uncertainty principle, which showed that certain pairs of properties, such as position and momentum, cannot both be known with unlimited precision at the same time. Erwin Schrödinger introduced wave mechanics and the famous equation that describes how quantum systems evolve. Between them, and with many others besides, the old image of matter as tiny hard bits moving along exact paths gave way to something subtler, stranger, and far more powerful. What makes all of this so remarkable is not simply that the quantum world is weird. It is that the weirdness is doing the work. The stability of atoms depends on quantum rules. The behaviour of electrons in those atoms determines chemistry. Chemistry gives rise to molecules. Molecules build solids, liquids, gases, cells, tissues, oceans, atmospheres, and bodies. The colours seen in leaves, paint, gemstones, and sunsets depend on how light interacts with matter at the quantum level. The firmness of a chair is not proof that the universe is simple. In a sense, it is proof that the universe is quantum and that quantum rules, when repeated on enormous scales, can produce something that feels reassuringly ordinary. Even the emptiness of matter is deceptive. Atoms are mostly space. Their nuclei are tiny compared with the size of the atom as a whole. If an atom were enlarged to the size of a cathedral, the nucleus would still be tiny by comparison, while the electrons would occupy a diffuse region around it. And yet tables do not behave like fog, and walls do not politely allow people to stroll through them on a thoughtful evening. Matter feels solid because of electromagnetic interactions and quantum principles, especially the behaviour of electrons and the Pauli exclusion principle, which prevents certain particles from piling into the same state. The world feels substantial not because it is made of miniature marbles packed together tightly, but because quantum mechanics gives matter structure and resistance. That is the hidden physics beneath ordinary life. Not a separate reality tucked away in some inaccessible corner, but the underlying logic of the one already here. The visible world is the large-scale expression of a much stranger microscopic world, one whose rules are not usually visible because they are so successful. Quantum mechanics does not constantly announce itself with dramatic fanfare. It simply goes on building atoms, shaping light, governing bonds, and quietly holding the world together. So when reality seems calm and sensible, that calmness is not the absence of strangeness. It is the result of strangeness organized with astonishing consistency. Beneath the smooth surfaces of daily life, beneath the air, the skin, the sunlight, and the silence, nature is doing something far more peculiar than it first appears, and it has been doing it all along. By the end of the 19th century, physics looked almost finished. Not completely finished, perhaps, because scientists are rarely reckless enough to say a subject is done when the universe is still sitting there unsolved, but finished enough to give that impression. Isaac Newton had explained motion and gravity. James Clerk Maxwell had unified electricity, magnetism, and light into one elegant framework. Thermodynamics had clarified heat, work, and energy. Across Europe, in universities and laboratories from Cambridge to Berlin, from Paris to Leyden, the physical world seemed to be yielding its secrets with admirable discipline. For large objects, this confidence was well earned. Classical physics could describe the swing of a pendulum, the path of a cannonball, the motion of planets, the pressure of gases, the spread of waves, and the flow of currents with remarkable accuracy. It offered a universe that felt structured, measurable, and above all predictable. If the position and speed of an object were known, then in principle its future path could be worked out. Nature appeared to be a grand machine, intricate but comprehensible, and it was easy to imagine that only a few small details remained to be tidied up. Then the small world began to misbehave. The trouble appeared whenever physicists looked too closely at atoms, radiation, and the behaviour of matter at very small scales. There, the old rules still seemed to gesture in the right direction, but they no longer landed cleanly. The mathematics that worked so beautifully for planets and projectiles began to fail when applied to glowing objects, electrons, and the structure of atoms. Classical certainty did not collapse all at once. It cracked, then splintered, then quietly became unusable in places where it had once seemed untouchable. One of the most important problems concerned blackbody radiation. A blackbody is an ideal object that absorbs all incoming radiation and then emits energy in a pattern determined only by its temperature. This may sound slightly niche at first, but it matters enormously because it is tied to something very ordinary. Anything with a temperature above absolute zero emits radiation. A stove, a candle flame, a human body, a star, and the warm wall of a room all radiate energy. Understanding this process was not a strange side quest. It was part of understanding heat, light, and matter themselves. Classical physics predicted the wrong pattern for this radiation. Worse than that, it predicted a disaster. At short wavelengths, the equation suggested that a hot object should emit more and more energy without limit. This result became known as the ultraviolet catastrophe, which is an excellent name because it sounds both scientific and slightly theatrical. Nature, however, refused to perform accordingly. Real objects did not release infinite energy. Experimental measurements showed a curve that rose, peaked, and then dropped away. The theory and the evidence did not match. In 1900, Max Planck found a way to reproduce the observed pattern. He proposed that energy is not exchanged in an endlessly smooth flow, but in discrete packets. These tiny units of energy would later be called quanta. Planck did not begin by announcing that all of reality was about to become strange. In fact, he was trying to solve a specific technical problem. But the solution carried a much deeper implication. If energy came in little bundles rather than in any arbitrary amount, then one of the smooth assumptions of classical physics had failed at a fundamental level. That was the beginning of a change in worldview. The old picture had imagined energy as something that could vary continuously, rather like the dimming and brightening of a lamp by infinitely fine degrees. Planck's results suggested that, at the microscopic level, nature might be more like a staircase than a ramp. Not always visibly so, not in any crude everyday sense, but in its basic transactions. The universe, it seemed, was not simply humming along in one continuous blur. It was counting. A few years later, Albert Einstein pushed this break much further. In 1905, he explained the photoelectric effect, an experimental result in which light striking a metal surface can eject electrons. Classical wave theory predicted that brighter light, regardless of colour, should eventually shake electrons loose if enough energy was delivered, but that was not what experiments showed. Instead, below a certain frequency, no electrons were emitted at all, no matter how intense the light became. Above that threshold, electrons were ejected promptly. Einstein explained this by treating light itself as quantized. Rather than behaving only as a continuous wave spread smoothly through space, light also acts as if it is made of localized packets of energy. Each packet, later called a photon, carries an amount of energy tied to the light's frequency. If a photon has enough energy, it can free an electron from the metal. If it does not, then flooding the surface with more low-energy light will not help. It is a little like trying to pay an entrance fee with a mountain of useless coupons when the door requires one valid ticket. This was a radical suggestion. Light had been strongly established as a wave through experiments involving interference and diffraction, yet now it seemed to have particle-like properties as well. Nature was refusing to stay in the neat conceptual boxes classical physics had prepared for it. Something similar would later happen with matter itself, but even at this stage the message was unsettling enough. The old framework was not merely incomplete in some decorative way, it was missing part of reality's grammar. These developments mattered far beyond theory. Light, heat, and colour were not abstract curiosities. They were woven into daily life. The warmth of sunlight, the glow of hot metal, the colours of objects, and eventually the operation of electronic devices, all depended on processes that classical ideas could not fully explain. The failure of the old picture was not confined to blackboards and lecture halls. It reached into the behaviour of the physical world all around us. This transformation unfolded in a broader scientific culture that was unusually rich and interconnected. European universities and research centres had become places of intense exchange, competition and refinement. Berlin, Munich, Copenhagen, Cambridge, Paris, Zurich and Leiden all played roles in shaping the emerging picture. Physicists argued, calculated, measured, corrected one another, and occasionally made reality sound less reasonable than it had the previous week. Out of that environment came a new framework, one that did not replace classical physics everywhere, but revealed its limits with uncomfortable precision. That is what it means to say classical physics started to break. It did not stop being useful. It remained brilliant for large systems and familiar scales. But when scientists pressed inward toward atoms, radiation, and tiny interactions, the old certainty began to fracture. Only then could the hidden quantum structure beneath ordinary life start to come into view. For most of human history, matter looked continuous. A lump of iron seemed like a lump all the way through. Water looked like water throughout. Stone, wood, air, gold, salt, skin, smoke, Each appeared to be its own kind of substance, smooth and uninterrupted unless broken into smaller visible pieces. If something could be chopped, ground, melted, or dissolved, it still felt as though the process was simply dividing one continuous material into smaller portions of the same thing. The deeper structure, if there was one, remained hidden. The idea that matter might be built from tiny indivisible units is very old. In the ancient world, thinkers such as Democritus imagined that reality might be made from small basic pieces moving through empty space. It was a striking idea, but it remained philosophy rather than science. There were no instruments capable of seeing atoms, no experimental framework to test them, and no reliable way to connect the idea to the behaviour of real substances. For a long time, atoms were less a discovery than an elegant guess. What changed was chemistry. By the early 19th century, chemists had begun to notice that substances combine in regular, repeatable proportions. Water was not a vague blend of ingredients. It formed from hydrogen and oxygen in a fixed relationship. Carbon dioxide, ammonia, and countless other compounds also followed clear patterns. This was difficult to explain if matter were perfectly continuous and infinitely divisible. In 1803, John Dalton proposed a modern atomic theory to account for these regularities. He suggested that each chemical element consists of its own kind of atom. The atoms of different elements differ in mass and properties, and that compounds form when atoms combine in simple numerical ratios. Dalton's atoms were not yet the richly structured atoms known today. They were more like useful building blocks in a chemical accounting system. Still, the power of the idea was enormous. It helped explain why substances combine in fixed proportions, why reactions produce predictable outcomes, and why matter can be rearranged without being created from nothing in the ordinary chemical sense. Suddenly, the visible world of powders, gases, crystals, and liquids no longer looked like a smooth blur of material. It looked arranged. That shift changed how ordinary matter was understood. Wood differed from iron, and iron differed from glass, not because each substance was some mysterious continuous essence, but because each was built from different atoms or different arrangements of atoms. Reactions were not magical transformations. They were reorganizations of tiny units. The world began to look less like a set of undivided materials and more like a vast architecture of microscopic parts. Then came the periodic table. In 1869, Dmitri Mendeleev organized the known chemical elements into a pattern based on their recurring properties. This was more than clever filing. It suggested that the elements were not a random list but members of a deeper order. The periodic table grouped substances by behaviour, hinted at missing elements not yet discovered, and implied that atomic identity followed rules. Later developments would show that this order reflects internal atomic structure, but even before that, Mendeleev's table made the atomic view of matter far more convincing. It is hard to believe matter is shapeless when the elements line themselves up with such suspicious elegance. Another powerful line of evidence came from spectroscopy, the study of light emitted or absorbed by substances. When heated gases were examined through prisms, they did not produce a smooth rainbow alone. Instead, they showed distinct lines at specific wavelengths. Hydrogen produced one pattern, sodium another, helium another still. Each element left a kind of optical fingerprint. This was a profound clue. It meant atoms were not just useful bookkeeping devices in chemistry. They had internal rules that determined how they interacted with light. Matter was announcing its structure through colour. Even so, some scientists remained cautious. Atoms were useful, yes, but were they physically real or merely convenient theoretical tools? That question lingered into the late 19th century. The answer arrived through a phenomenon so humble it might easily have been ignored: Brownian motion. Brownian motion is the jittery, irregular movement of tiny particles suspended in a fluid, such as pollen grains in water. The botanist Robert Brown observed it in the 19th century, but the deeper meaning was not immediately clear. In 1905, Albert Einstein gave it a powerful explanation. He showed that if liquids are made of countless invisible molecules in constant random motion, then those molecules would buffet suspended particles from all sides, producing exactly the erratic dance seen under a microscope. Brownian motion was not just visual noise. It was visible evidence of invisible collisions. Einstein's work made atomic theory testable in a more direct way. Soon afterward, Perrin carried out careful experiments on Brownian motion and used them to estimate quantities related to atoms and molecules. His results strongly supported Einstein's explanation and helped convince the scientific world that atoms were not philosophical decoration. They were real components of matter, not imagined, not metaphorical, not merely useful but physically there. This transformed the understanding of everyday reality. A glass of water was no longer a continuous volume, but an immense collection of molecules in motion. A grain of salt was an ordered lattice of atoms. Air became a restless mixture of molecules colliding at high speed. A metal spoon, a wooden door, a lungful of breath, a drop of rain, all were built from countless tiny units with specific masses, arrangements, and behaviours. Even a very small amount of matter contains an astonishing number of atoms. A single drop of water holds far more molecules than there are people on Earth, which is a pleasing reminder that the ordinary world is quite extravagant under the surface. So the question raised by the failure of classical ideas about light and energy led naturally to a deeper one. What is matter actually made of? The answer was not a smooth substance without inner structure. It was atoms, then molecules, then patterns, bonds, and arrangements. The world only appears continuous because the pieces are far too small to see directly. Beneath the calm surfaces of daily life, matter is particulate, ordered, and endlessly busy. Once atoms had become real, another question became impossible to ignore. If matter is built from tiny units, what exactly is light doing when it meets them? Light is everywhere in ordinary life. It warms skin, carries colour, powers photosynthesis, reflects from walls, passes through windows, and reaches the eye with such effortless familiarity that it rarely feels mysterious at all. And yet, light turned out to be one of the strangest things in physics because it refused to behave as only one kind of thing. For a long time, light seemed most convincingly like a wave. Waves were already a familiar part of life. Water ripples spread across a pond. Sound moves through air in compressions and rarefactions. A rope flicked at one end carries a travelling disturbance. Light seemed to fit naturally into that family. It could reflect, refract, and spread. It could bend around edges and pass through narrow openings in ways that suggested something extended and undulating rather than something compact and pellet-like. One of the clearest demonstrations came from interference. In the early 19th century, Thomas Young showed that when light passes through two closely spaced slits, it does not simply form two bright patches on a screen. Instead, it creates a pattern of alternating bright and dark bands. This happens because waves can reinforce each other where crest meets crest, and cancel where crest meets trough. The result is an interference, pattern, and it is very difficult to explain with the idea of light as a stream of tiny classical particles. Diffraction told a similar story. Light bends and spreads when it encounters edges or narrow openings, again behaving in the graceful, slightly unbothered manner of a wave. By the late 19th century, this wave picture had become deeply persuasive. James Clerk Maxwell had shown that light is an electromagnetic wave, part of a larger family that includes radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. That was a tremendous achievement. It connected light to electricity and magnetism and gave physics a powerful unified framework. It seemed, for a while, that the matter was settled. Then light began to misbehave again. The trouble emerged when scientists studied the interaction between light and matter more closely. Max Planck, while working on blackbody radiation in 1900, found that energy had to be exchanged in discrete packets to match experiment. That was already a serious crack in the old picture. But it was Albert Einstein, in 1905, who took the bolder step. To explain the photoelectric effect, he proposed that light itself behaves as if it comes in individual quanta of energy. The photoelectric effect is simple to describe but profound in meaning. Shine light on a metal surface, and under the right conditions electrons are ejected. Classical wave theory suggested that brighter light should eventually knock electrons free, because brightness means more energy. But experiments showed something more specific and much stranger. The colour of the light, or more precisely its frequency, was decisive. Below a certain frequency, no electrons came out at all, no matter how intense the light became. Above that threshold, electrons were emitted quickly. Einstein explained this by treating light as if it arrives in individual packets, later called photons. Each photon carries a specific amount of energy, and that energy depends on frequency. Blue light and ultraviolet light carry more energy per photon than red light. If a photon delivers enough energy to overcome the binding energy holding an electron in the metal, the electron escapes. If it does not, then increasing the number of low-energy photons does not solve the problem. 100 polite knocks on a locked door do not equal one key. That was the remarkable conclusion. Light behaves like a wave in some experiments and like a collection of particles in others. Not because physicists were being indecisive, and not because the universe enjoys being awkward for the sake of it, though it sometimes gives that impression, but because neither older category was sufficient on its own. Light required a dual description. This became known as wave-particle duality. That phrase can sound neat and tidy, but the reality it points to is not especially tidy at first glance. Waves are spread out, particles are localized, waves interfere, particles arrive as individual events, and yet light does both. A beam can produce an interference pattern showing its wave-like nature, while also being detected in individual photons, each interacting as a discrete packet of energy. The deeper lesson was that nature does not always organize itself according to the categories human intuition prefers. Light is not a wave one day and a particle the next, as though it checks the calendar. It is quantum object, and the way it reveals itself depends on how it is measured and how it interacts. This matters because light is not some distant curiosity confined to observatories and laboratory benches. Ordinary sight depends on it. Colour depends on it. Warmth from the sun depends on it. The glow of heated objects, the operation of solar cells, the behaviour of camera sensors, the chemistry of photosynthesis, the structure of spectroscopy, and the very process by which the eye detects incoming light all rely on this quantum nature. Vision itself begins with photons interacting with molecules in the retina. In that sense, every act of seeing is already an encounter with quantum behaviour. The world looks the way it does because light and matter are in constant conversation. Photons are absorbed, emitted, scattered, reflected, and transmitted depending on the structure of atoms and molecules. Colour is not painted onto objects by some decorative force from outside. It arises because matter interacts with different wavelengths of light in different ways. Warmth from sunlight is not a vague atmospheric gift. It is energy carried by electromagnetic radiation and transferred through quantum interactions. Even a simple bright morning is, underneath its pleasant lack of drama, a continuous exchange between matter and quantized light. So the discovery that matter is atomic naturally led into this deeper realization. Atoms are real, but atoms do not sit in darkness. They are constantly interacting with radiation, and the radiation itself turned out to be just as strange as the matter it meets. Light had to be understood as both wave-like and particle-like before the modern picture of reality could begin to hold together. That insight changed science permanently. It also quietly changed the meaning of the ordinary world. Sunlight on a floor, a colour in a leaf, the warmth of skin, the image entering an eye, none of these are simple in the old classical sense. They are familiar expressions of a deeper quantum order. And once light had been forced out of its old category, another unsettling possibility began to emerge. Perhaps light was not the only thing refusing to behave like either a wave or a particle. Perhaps matter itself was about to become stranger too. Once light had refused to stay in a single category, the next question arrived with slightly alarming force. Was that strangeness unique to light, or was it telling us something broader about nature itself? For a while, there was still room to hope that photons were the odd ones out. Light had always been a little theatrical. It travelled at a fixed speed, behaved as an electromagnetic wave, and already seemed different from lumps of matter. But that comforting separation did not last. It turned out that matter too was unwilling to behave like a neat collection of tiny solid objects. The classical picture had imagined particles rather simply. A particle was supposed to be like a minuscule billiard ball, perhaps too small to see, but still a thing with a definite position and a definite path. If left alone, it would travel from one place to another in a clear trajectory. That idea works well enough for thrown stones, cannonballs, raindrops, and planets. It even feels emotionally satisfying. Human intuition likes objects that know where they're going. Quantum physics, unfortunately, had other plans. In the 1920s, the French physicist Louis de Broglie proposed a remarkable idea. If light, which had long been treated as a wave, could also behave like a particle, then perhaps matter, which had long been treated as particulate, could also behave like a wave. It was a bold symmetry. De Broglie suggested that every particle with momentum has an associated wavelength. Not metaphorically, not as a poetic flourish, but physically. Matter itself might possess wave-like properties. At first glance, this sounds absurd in a very understandable way. A wave of what exactly? A wave on what? An electron is not a water ripple and not a vibrating string. Yet the suggestion was not that matter becomes a classical wave made of some visible medium. The claim was deeper than that. The mathematical description of matter had to include wavelength, interference, and other wave-like features. Electrons were not little pebbles moving through space on tidy tracks. They had a behaviour that could spread, overlap, and interfere. The crucial point is scale. De Broglie wavelengths are significant for very small particles because their momentum can be very small. For large objects, the wavelength becomes so tiny that wave effects are effectively invisible. A rolling football also has a de Broglie wavelength, which is a wonderful detail because it means the universe is committed to its principles even when no one asks for the joke. But that wavelength is so unimaginably small that no football has ever produced a visible interference pattern on a pitch. Electrons, by contrast, are light enough that their wave nature matters enormously. The idea soon moved from theory to experiment. In the later 1920s, Clinton Davison and Lester Germer in the United States were studying how electrons scattered from a nickel crystal. What they found was not the behaviour expected from classical particles simply bouncing off a surface. Instead, the scattered electrons produced a pattern characteristic of diffraction, the kind of spreading and interference associated with waves. The crystal acted rather like a diffraction grating, and the electrons responded in exactly the way de Broglie's proposal suggested they should. Around the same time, George Paget Thompson in Britain carried out related experiments in which electrons passed through thin metal films and produced diffraction patterns as well. This was an extraordinary moment in science. Light, once thought securely wave-like, had revealed particle behaviour. Matter, once thought securely particle-like, had revealed wave behaviour. Nature had crossed the categories from both directions and made the old distinction look far less fundamental than people had assumed. This changed everything. If electrons behave as waves, then they cannot be understood as tiny hard pellets orbiting an atomic nucleus in neat little circles. That older image had always been a bit too charming to survive serious scrutiny. Wave behaviour meant that electrons in atoms must occupy allowed patterns rather than arbitrary miniature trajectories. That insight became central to atomic structure. The stability of atoms, the arrangement of electrons, and the existence of distinct energy levels all depend on the fact that electrons are described by quantum wave behaviour. It also matters for chemical bonding. Atoms combine because electrons can occupy shared quantum states that lower the total energy of the system. Molecules are not built by atoms hooking together with microscopic enthusiasm. They form because electron waves and allowed energy states make certain arrangements stable. The shape of water molecules, the strength of carbon bonds, the behaviour of metals, the properties of proteins, the structure of minerals, all of this depends on the quantum nature of electrons. Chemistry works because matter is not classical at small scales. Conductivity depends on it as well. In metals, some electrons are able to move through the material in ways that reflect quantum states spread across many atoms. In semiconductors, the story becomes even more delicate, with band structures and energy gaps determining whether electrons can move under particular conditions. Modern electronics, from computer chips to solar cells, rest on this behaviour. If electrons were only tiny classical pellets, the materials of the modern world would not behave as they do. Even the basic stability of matter is tied to this strangeness. If particles behaved in a purely classical way, atoms would not hold together properly, and solids would not possess the properties they do. The ordinary world depends on quantum rules operating beneath notice. Chairs feel solid, metals conduct, molecules persist, crystals form, and biological structures endure because electrons are governed by wave mechanics rather than classical certainty. This is the strange comfort of it all. The familiar world exists because matter refuses to behave like tiny billiard balls. The calm stability of everyday life is not built on a simple mechanical foundation. It is built on a subtler one, in which particles are also waves, in which allowed states matter more than imagined paths, and in which the microscopic world follows rules that no one would have guessed from watching apples fall or dust drift in sunlight. So the quantum picture became broader and harder to ignore. First light had to be described in two ways at once, then matter joined it. Wave-particle duality was no longer a peculiar feature of radiation alone. It had become a general lesson about the physical world. And once electrons were understood in this way, the structure of atoms, the nature of chemistry, and the behaviour of ordinary materials could begin to make sense in a new and far more powerful way. By the time electrons had begun behaving like waves, the atom could no longer be pictured as a tiny mechanical solar system without causing trouble. That older image had been tempting for obvious reasons. It was neat, visual, and slightly flattering to human intuition. A small dense nucleus, in the middle electrons circling around it like planets around a star, all very orderly and dignified. The difficulty was that classical physics did not permit such an arrangement to survive. An electron carries negative electric charge. The nucleus, because of its protons, carries positive charge. Opposite charges attract. So far, so sensible. But in classical electromagnetism, a charged particle moving in a curved path should emit radiation and lose energy. That means an electron orbiting a nucleus ought to radiate energy continuously, spiral inward, and crash into the nucleus in a tiny fraction of a second. If atoms really behaved that way, stable matter would not exist. Chemistry would not exist. Solids, liquids, cells, and anyone trying to quietly enjoy a glass of water would be out of luck. And yet atoms do exist. They persist. They build the world with almost unreasonable reliability. So something in the classical picture had to be wrong. This was not a small technical inconvenience. It was a foundational problem. The atom had become real through chemistry and experiment, but its internal structure still needed an explanation that did not immediately destroy it. Once matter had been shown to behave in wave-like ways, that explanation finally began to emerge. A major step came in 1913 with Niels Bohr. Working from Ernest Rutherford's nuclear model of the atom, in which a tiny central nucleus contains most of the mass, Bohr proposed that electrons can occupy only certain allowed orbits with specific energies. They do not wander continuously through any possible path. Instead, they exist in discrete energy states. While in one of these allowed states, an electron does not radiate energy in the way classical theory would predict. It can move between states, but only by absorbing or emitting a precise amount of energy. Bohr's model was not the final description of the atom, but it was a breakthrough because it captured something crucial. Atomic energy is quantized. Electrons are not free to sit anywhere they please. The atom has structure because only certain arrangements are allowed. This helped explain one of the most revealing clues in all of early atomic physics: emission spectra. When atoms are heated or otherwise energized, they can emit light. But they do not produce a smooth spread of all colors. Instead, they produce sharp lines at specific wavelengths. Each element has its own distinct pattern. Hydrogen has one set of lines, helium another, sodium another still. These spectral lines were measured with increasing precision in laboratories across Europe, using spectroscopes that separated light into its component wavelengths. Spectroscopy became one of the great windows into atomic structure, because it showed that atoms have internal rules. Hydrogen was especially important because it is the simplest atom, with one proton and one electron. That simplicity made it the ideal testing ground. Bohr's model successfully explained the main spectral lines of hydrogen by linking them to jumps between allowed energy levels. When an electron moved from a higher energy state to a lower energy one, the atom emitted a photon with an energy equal to the difference between those levels. The color of the emitted light was therefore not arbitrary. It reflected the architecture of the atom itself. That was an extraordinary shift in understanding. Color was no longer just a property seen by the eye. it became evidence about atomic structure. The light from an atom could be read like a record of its internal arrangement. Still, Bohr's atom was only an intermediate step. It retained the idea of electrons moving in little orbits, which was useful at first but ultimately too classical to survive. The deeper quantum view replaced those orbits with quantized states described by wave mechanics. Once electrons were understood as having wave-like behaviour, their place in the atom could no longer be imagined as a miniature planet tracing a definite ring. Instead, the electron had to be described through allowed standing wave patterns associated with specific energies. That change mattered enormously because it answered the basic question of atomic stability in a more natural way. The atom does not collapse because the electron is not a tiny bead that ought to lose energy and fall inward under classical rules. It is part of a quantum system in which only certain states are possible, and the lowest allowed state still has a finite extent. In other words, quantum mechanics prevents the electron from simply settling into the nucleus because the structure of the system does not permit that outcome in the way classical intuition expects. This is where the architecture of matter truly begins. Atoms are stable not by accident, and not because the universe kindly overlooks a flaw in the equations. They are stable because quantum rules create structured, quantized arrangements that can persist. Those arrangements give each element its identity. Hydrogen behaves like hydrogen because of the number of protons in its nucleus and the corresponding structure of its electron states. Carbon behaves like carbon. Oxygen behaves like oxygen. Gold behaves like gold. The periodic table is not a catalogue of mysterious essences. It is a map of stable atomic identities made possible by quantum structure. Once that is understood, the broader world begins to make more sense. Chemical elements differ because their atoms differ. Their spectra differ because their allowed energy levels differ. Their reactivity differs because their electrons occupy different arrangements. The material diversity of the visible world begins here in the stable quantum atom. It is worth pausing on how radical this was. Classical reasoning could describe falling bodies, orbiting planets, and vibrating strings, but it could not explain why atoms survive. Quantum theory could. It did not merely add a layer of decoration to the atom. It made the atom possible as a lasting structure. Without quantized energy levels, without allowed states, without the wave nature of electrons, matter as we know it would not hold together. So once matter was understood to behave like waves, the internal structure of atoms could finally be described in a way that matched reality. The atom stopped being a dangerously unstable miniature machine and became something richer, a quantum system with permitted states, measurable spectra, and enduring form. And from that stable beginning came everything built from atoms afterward, from minerals and metals to oceans, proteins, lungs, leaves, and light-sensitive eyes. Everyday reality begins to look ordinary only after the quantum atom has already done the difficult work. It is one thing to say that atoms are stable. It is another to ask why. Once the atom was understood as a tiny nucleus surrounded by electrons, the central problem became impossible to ignore. Negative electrons are attracted to the positive nucleus. In classical physics, that attraction ought to pull the electron inward. A moving charged particle should also radiate energy, which means it should lose energy as it goes. Put those ideas together, and the result is grim for matter. The electron should spiral inward and collapse into the nucleus. The atom should not last, and yet atoms do last. They last so well, in fact, that they make furniture, lungs, rainwater, limestone, and people with opinions. So the question is not a trivial one. Why does the electron not simply fall in? The answer lies in the fact that the electron is not a tiny marble flying around a central point. Quantum mechanics replaces that picture with something stranger and more accurate. The electron in an atom is described by a quantum state. That state has a definite energy, and only certain energies are allowed. These are quantized states. The electron cannot take just any value of energy and sit just anywhere it likes. The atom permits certain arrangements and forbids others. A helpful way to picture this is through standing wave behaviour. A plucked string can only sustain certain patterns of vibration if both ends are fixed. It cannot vibrate in any random shape and remain stable. Something similar happens in the quantum atom. The electron behaves in a wave-like way, and only certain standing wave patterns fit the atomic system. Those allowed patterns correspond to allowed states. The lowest of those states is not the nucleus itself. It has a finite size and a finite energy. In other words, the most stable state available to the electron is still spread out rather than collapsed into a central point. This is one of the deepest differences between classical and quantum reasoning. Classical intuition imagines the electron as an object with a path. Quantum mechanics describes a structure of possibilities with allowed states. The atom does not survive because the electron somehow resists attraction out of stubbornness. It survives because the rules of the system do not permit the classical collapse that intuition expects. This becomes even clearer with Werner Heisenberg's uncertainty principle. In broad terms, the uncertainty principle says that position and momentum cannot both be known with unlimited precision at the same time. The more precisely one is defined, the less precisely the other can be defined. This is not a statement about clumsy equipment, poor microscopes, or scientists sneezing at crucial moments. It is not a temporary flaw in measurement. It is built into the structure of quantum reality itself. That matters enormously for atomic stability. If an electron were forced into an extremely tiny region right at the nucleus, its position would become very tightly confined. According to the uncertainty principle, that would mean a very large uncertainty in momentum. In practice, that corresponds to very high kinetic energy. So squeezing the electron too tightly does not produce a calm low-energy collapse. It drives the energy upward. The atom reaches stability in a lowest allowed state that balances these quantum constraints. It cannot simply shrink without cost. This is why the uncertainty principle is so important. It is often introduced as a curious feature of measurement, but it is really part of the architecture of matter. It helps explain why atoms have size, why electrons occupy extended states, and why the material world is not reduced to a featureless pile of collapsed charge. Stable chemistry depends on this. Stable solids depend on it. Living matter depends on it. If electrons could simply fall into nuclei, there would be no persistent atoms to combine, no molecules to build tissues, no reliable structure for matter at all. This broader way of thinking became part of what is often called the Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg. In that view, quantum systems are described in terms of allowed states, probabilities, and measurable outcomes rather than tiny hidden classical trajectories. That does not mean the atom is vague in the everyday sense. It means the old demand for a precise little path is the wrong question. The electron is real, the atom is real, and the structure is real, but the reality involved is quantum rather than classical. This gives the atom its durability. The previous picture of the quantum atom explained that electrons occupy quantized states. The deeper point is why those states do not dissolve into collapse. Quantization, standing wave behaviour, and the uncertainty principle together prevent that outcome. The atom endures because quantum mechanics does not allow the electron to behave like a shrinking classical object on a doomed spiral. That is why this strange theory matters so much to ordinary life. It is not merely a theory of tiny oddities in remote laboratory conditions. It is the reason stable matter exists at all. The chemistry of water, the solidity of stone, the structure of proteins, the persistence of air, the possibility of living cells, all rest on the fact that electrons do not fall into the nucleus. Everyday reality feels calm only because the quantum world has already solved the problem underneath it. Once the atom had been rescued from collapse, a new question took its place. If electrons do not travel around the nucleus like tiny planets, then what exactly are they doing? The old image of orbiting electrons is memorable, simple, and very nearly wrong in the ways that matter most. It is useful in the same way a stick figure is useful for understanding human anatomy. One can tell what it is meant to represent, but it will not get anyone through medical school. Quantum mechanics replaces the idea of electron orbits with something subtler. Instead of neat little tracks, it gives orbitals. An orbital is not a tiny road, and it is not a miniature ring circling the nucleus. It is a mathematical description of where an electron is likely to be found, based on the quantum state of the atom. That means an orbital is a probability distribution. It describes patterns of likelihood rather than a fixed path. The electron does not move around the nucleus in a little loop that could be drawn like the orbit of Mercury. What exists instead is a structured cloud of possibility governed by wave mechanics. This shift is one of the most important in all of modern science, because it changes the atom from a crude mechanical picture into a stable quantum architecture. The electron is described by a wave function, and the allowed wave functions in an atom form standing wave solutions. These solutions are not arbitrary. They arise from the conditions inside the atom, especially the attraction between the negatively charged electron and the positively charged nucleus. Only certain patterns are allowed, and each pattern corresponds to a particular energy. This is where Schrödinger enters the story. In the 1920s, Schrödinger developed wave mechanics and introduced what became known as the Schrödinger equation. In descriptive terms, that equation provides a way to calculate how quantum states behave and how they evolve. For atoms, it allows physicists to determine the allowed states of electrons and the spatial patterns associated with these states. It turns the quantum atom into something that can be worked out, tested, and related to observation, rather than merely admired for its strangeness. The solutions to the Schrödinger equation for atoms produce orbitals with different shapes and energies. Some are spherically distributed around the nucleus. Others form more directional patterns with lobes extending through space. These shapes are not decoration. They are the deep reason matter has structure. The way electrons are arranged in these orbitals determines how atoms interact, how they bond, and how they build the ordinary substances that make up the visible world. This also helps explain the periodic table in a much deeper way than simple listing ever could. The periodic table is not just a catalogue of elements arranged in tidy rows because chemists enjoy order, although many of them certainly do. Its structure reflects the filling of electron states. As electrons are added to atoms, they occupy orbitals in a specific order governed by energy and quantum rules. That is why elements repeat patterns of chemical behaviour. Sodium and potassium behave similarly because their outer electron arrangements share an important structure. Neon is unreactive because its outer shell is full. Carbon forms rich, versatile bonds because of the particular arrangement of its electrons. The periodic table is, in a real sense, a map of quantum architecture. Another essential figure here is Wolfgang Pauli. Pauli introduced the Pauli exclusion principle, one of the most quietly powerful ideas in physics. It states that no two, electrons in the same atom can occupy the same quantum state. This sounds technical, but its consequences are enormous. It means electrons must stack into distinct allowed states, rather than collapsing into one identical lowest condition. That is why atoms develop layered electron structures. It is why shells and subshells exist. It is why the elements display recurring chemical properties, rather than all behaving as slight variations of the same anonymous blob. The exclusion principle is one of the main reasons matter has texture and layering at all. Without it, electrons would all crowd into the lowest possible state, and the world would not have the same diversity or stability. Chemistry would be radically altered. Solids would not behave as they do. The familiar variety of matter would be lost. In a very real sense, the richness of ordinary substances depends on the fact that electrons are orderly in a rather stern quantum way. They are not allowed to all sit on each other and call it a day. Once orbitals and the exclusion principle are taken seriously, the visible world starts to look less mysterious in one sense and more mysterious in another. The textures of materials, the strengths of bonds, the shapes molecules prefer, and the reactivities of different substances all emerge from invisible electron arrangements. Diamond is hard because of the way carbon atoms bond in a rigid three-dimensional network. Graphite is soft and slippery because the same element, carbon, arranges its electrons and bonds differently. Metals conduct electricity because some of their electrons occupy states that allow motion through the structure. Insulators resist conduction because their electron arrangements do not permit that motion easily. Water has its peculiar properties because of the geometry of its molecule and the distribution of charge created by its electron structure. In other words, the shape of matter begins long before matter becomes visible. It begins with patterns of probability, allowed states, and the occupation of orbitals. The world of tables, stones, leaves, lungs, bones, glass, paper, and skin is built from these hidden arrangements. What seems solid and obvious at human scale is the large-scale result of quantum patterns too small to see directly. This is why the transition from atomic stability to atomic structure matters so much. Once it was clear that electrons do not collapse into the nucleus, the next task was to understand how they are arranged. Orbitals answered that question. They revealed that the inside of the atom is not a miniature solar system, but a structured quantum pattern. That pattern gives rise to the periodic table, to chemical diversity, and to the layered complexity of matter. So the visible diversity of the everyday world begins in a place that cannot be directly seen. It begins with orbitals, with wave functions, with Schrödinger's equation, and with the stern organizing power of Wolfgang Pauli's exclusion principle. The colors, textures, strengths, and reactions of ordinary materials are not surface features added afterward. They are consequences of the internal quantum design of atoms. Everyday reality once again turns out to be built from something much stranger than it first appears. Once the internal structure of atoms had begun to make sense, the next question was almost impossible to avoid. How do atoms join? Why do they not simply remain isolated, each keeping its electrons to itself in dignified solitude? Why does hydrogen combine with oxygen to make water? Why does carbon build elaborate chains? Why does sodium react so eagerly with chlorine? And why do metals behave like metals instead of politely becoming piles of separate atoms? The old instinctive answer might be to imagine atoms sticking together like tiny mechanical parts, little hooks, little catches, little snap-fit pieces. It is an appealing image, partly because it sounds practical and partly because it makes chemistry feel like microscopic carpentry. But that is not how bonding works. Atoms do not cling to one another because they happen to be shaped like cooperative Lego bricks. Chemical bonds arise from electron behaviour, from allowed quantum states, and from the tendency of systems to move toward lower energy arrangements. That last point matters. In physics and chemistry, stable structures tend to be the ones with lower total energy. This does not mean nature has ambitions or preferences in any conscious sense. It means that some arrangements are more stable than others, and those are the arrangements that persist. When atoms come together, the electrons and nuclei in the combined system can sometimes settle into a configuration with lower energy than the atoms would have separately. When that happens, a bond forms. Chemistry is not matter sticking by accident. It is matter finding stable quantum arrangements. The reason electrons are central is that they occupy the outer regions of atoms and determine how atoms interact with one another. The nucleus sets the identity of the element by the number of protons it contains, but the electrons, especially the outermost electrons, determine much of the chemistry. Their allowed states, their spatial distributions, and their energies govern whether atoms attract, repel, share, transfer, or organize themselves into larger structures. Chemistry is therefore a direct consequence of quantum structure. One major kind of bonding is ionic bonding. This happens when one atom gives up one or more electrons and another atom accepts them. The result is not a pair of neutral atoms anymore, but two ions with opposite electric charges. A positively charged ion and a negatively charged ion attract each other strongly through electromagnetism. Sodium chloride, ordinary table salt, is a classic example. A sodium atom can lose an electron relatively easily, while a chlorine atom can gain one. The resulting ions arrange themselves into a crystal lattice, a repeating structure held together by electrostatic attraction. Salt looks calm and harmless in a shaker, but its existence depends on electrons moving between atoms and leaving behind a precisely ordered pattern of charge. Another major kind is covalent bonding, and this is where chemistry becomes especially rich. In a covalent bond, atoms share electrons. But even that sentence can be misleading if it sounds too friendly or casual, as if atoms are taking turns with a communal object out of good manners. What really matters is that electrons can occupy shared quantum states spread across more than one nucleus. By doing so, the total energy of the system can be lowered, making the bonded arrangement stable. Hydrogen molecules form this way. So do water molecules, carbon dioxide molecules, and the enormous range of organic compounds built from carbon. Water is a particularly good example because it is so ordinary and so extraordinary at the same time. A water molecule consists of one oxygen atom bonded to two hydrogen atoms through covalent bonds. The specific arrangement of electrons gives the molecule its bent shape and its uneven distribution of charge. That uneven charge distribution makes water polar, meaning one side of the molecule is slightly more negative and the other slightly more positive. From that follow many of water's remarkable properties, including its ability to dissolve many substances, its high surface tension, and the hydrogen bonding that helps give ice its open crystalline structure. So even a glass of water, which appears about as uncontroversial as matter can get, is quietly displaying the consequences of quantum electron arrangement. Metallic bonding is different again. In metals, outer electrons are not tied to one specific pair of atoms, in the way they are in many covalent bonds. Instead, they can occupy states spread across large numbers of atoms in the metal structure. This helps explain why metals conduct electricity and heat so well, why they are often shiny, and why they can be shaped without immediately shattering. A metal is not just a pile of neutral atoms pressing shoulder to shoulder. It is a quantum-organized material in which electron states extend through the lattice in a way that gives the substance its familiar properties. This is why chemistry cannot be reduced to simple classical sticking. The bonds that hold matter together depend on quantum mechanics at every level. Electrons occupy orbitals, combine into molecular states, avoid one another according to the Pauli exclusion principle, and settle into arrangements governed by energy minimization. The geometry of molecules, the strength of materials, the reactivity of substances, and the enormous diversity of the chemical world all emerge from these quantum rules. Linus Pauling played a major role in making this picture clearer. He helped develop the understanding of chemical bonding in terms of quantum mechanics and showed how electron arrangement relates to molecular shape and structure. His work helped bridge physics and chemistry, showing that the behaviour of molecules is not a separate mystery floating above atomic theory. It grows directly out of it. Molecular structure is quantum structure expressed on a slightly larger stage, and this is where the title becomes especially tangible. Everyday reality becomes substance here. Water, air, proteins, plastics, salt, metals, and minerals are not abstract examples chosen for educational convenience. They are the world. Air is a mixture of molecules such as nitrogen and oxygen, each held together by quantum-governed bonds. Proteins are long chains of amino acids whose shapes and functions depend on specific atomic interactions. Plastics are built from repeating molecular units linked into polymers with distinct properties. Minerals are crystalline arrangements of atoms and ions formed through stable bonding patterns. Metals shape. Tools, wires, buildings, and machines because of the way their electrons behave collectively. Even living matter is chemistry made durable and intricate. Cells depend on membranes, enzymes, nucleic acids, sugars, and structural proteins, all of which are possible only because atoms bond in stable and highly specific ways. Civilization, too, rests on quantum chemistry. Stone, glass, steel, concrete, fuel, medicine, electronics, and synthetic materials all exist because electrons and nuclei can form the right structures under the right conditions. So once the inner arrangement of electrons in individual atoms had been understood, the next great step was to see how those electrons allow atoms to join into molecules and materials. That is the point at which the hidden quantum world becomes the everyday physical world in a more direct sense. Chemistry is the bridge. It is the process by which atomic structure becomes substance, by which quantum rules become water, salt, metal, air, skin, bone, wood, and everything else that fills ordinary life. The world feels solid and familiar not because it escaped quantum mechanics, but because quantum mechanics learned how to build with extraordinary patience. By the time atoms have bonded into molecules and materials, another question begins to press forward with suspicious persistence. Why does matter feel solid at all? A wooden table feels firm, a stone step resists a foot, a metal railing pushes back against a hand. Everything about ordinary experience suggests that solid objects are densely packed things, compact all the way through, with substance pressed tightly against substance. But that is not really what matter is like. Atoms are mostly empty space. A tiny nucleus sits at the centre, containing nearly all the atom's mass, while electrons occupy a much larger surrounding region, described by quantum states. If an atom were enlarged enormously, the nucleus would still be tiny by comparison, while the rest would be structured mostly by the presence of electron probability distributions rather than little hard bits stacked wall to wall. This leads to the natural and slightly irritating question of why a table does not feel like a vague mist. If matter is mostly empty space, why do solid things not behave more like apologetic fog? The answer is that solidity does not come from atoms being packed like featureless miniature stones. It comes from electromagnetic interactions and quantum exclusion effects. What feels like contact between surfaces is really a force-based encounter between the electron structures of atoms in one object and the electron structures of atoms in another. Matter feels solid not because the parts are densely stuffed, but because the underlying fields and quantum rules strongly resist certain kinds of overlap. Electromagnetism is the first part of the story. Electrons carry negative electric charge. When the outer electrons of atoms in a hand approach the outer electrons of atoms in a table, they repel one another. This is one aspect of the electromagnetic force, and it plays an enormous role in the stability and mechanical behaviour of ordinary matter. The sensation of pushing on a surface is not a literal meeting of tiny hard shells like marbles colliding. It is the result of charged quantum systems responding to one another at very short distances. But electromagnetism alone is not the whole story. The deeper firmness of matter also depends on the Pauli exclusion principle, introduced earlier in the story of atomic structure. Wolfgang Pauli showed that no two electrons can occupy the same quantum state in the same system. This principle is not an optional detail tucked away in specialist physics. It is one of the main reasons matter has layered structure, volume, and resistance. If electrons were all allowed to collapse into the same lowest energy state, atoms would not build matter in the same way, and the world would be unrecognizably different. This is why matter resists compression in ordinary conditions. When two collections of atoms are pushed close together, the electrons cannot all simply merge into identical states and let everything pass neatly through everything else. The exclusion principle forbids that. The available quantum states begin to fill, and forcing further overlap requires particles to occupy higher energy arrangements. That costs energy, and the system resists. In effect, matter pushes back because the quantum rules governing electrons do not allow unlimited crowding. This sounds abstract at first, but it is happening in every ordinary touch. When a hand rests on a table, the atoms in the skin do not truly crash into the nuclei of the atoms in the wood. Instead, electromagnetic repulsion and quantum exclusion prevent the electron structures from overlapping freely. The hand is supported because the table's matter is responding according to those rules. The table does not know how to be solid in any conscious sense. It simply cannot behave otherwise under the laws that govern its electrons. So the ordinary sensation of touching a floor or leaning against a wall is, at bottom, a direct encounter with quantum-organized matter and electromagnetic fields. It is not really contact in the old common-sense picture of solid lumps meeting flush against one another. It is a balance of forces and forbidden overlaps, enacted at unimaginably small scales, and then magnified upward into the familiar world of pressure, support, and resistance. This scales upward beautifully, which is one of the quieter marvels of physics. The same principles that keep electrons in structured atomic states also help give firmness to wood, stone, skin, glass, and metal. Wood feels solid because its atoms are arranged into large molecular and cellular structures whose electrons follow quantum rules. Stone resists because mineral lattices are held together by bonding and exclusion-governed atomic organization. Metal has its own kind of solidity, shaped by metallic bonding and electron behavior spread through a lattice. Skin feels soft compared with steel, of course, but even softness is a kind of organized resistance. A pillow yields more than a brick, yet neither allows a hand to pass through as though it were not there. That difference between soft and hard is not a difference between matter and non-matter. It is a difference in structure, bonding, and the way force is distributed across the material. Rubber, wood, flesh, and iron all feel different because of their atomic and molecular organization, but all of them derive their resistance from the same underlying principles of electromagnetic interaction and quantum mechanics. Even flexibility is built on firmness arranged in a particular way. This is why the question matters so much. Once chemistry has built substances, quantum rules also determine why those substances hold their shape and resist intrusion. Bonding creates the material. Electron structure and quantum exclusion help give it form, volume, and mechanical presence. The world of substances becomes the world of surfaces, and the world of surfaces becomes the world of daily experience. There is something quietly strange in that. The most obvious fact about a chair, namely that one can sit on it without falling through, is not explained by simple packedness. It is explained by invisible interactions among charged particles and by the exclusion principle, preventing electrons from all collapsing into the same arrangement. Solidity, one of the oldest and most trustworthy sensations in human life, turns out to be a quantum phenomenon wearing a very convincing disguise. So matter feels solid, not because atoms are tiny hard stones pressed tightly together, but because the quantum world does not allow matter to be otherwise. Electromagnetic repulsion keeps charged structures from merging freely. The Pauli exclusion principle prevents electrons from collapsing into identical states. From these microscopic rules comes the macroscopic firmness of floors, doors, bones, mountains, and hands. The world feels substantial because quantum mechanics is doing its work with extraordinary consistency, quietly turning mostly empty atoms into a universe full of surfaces that hold. Once matter has shape and solidity, another question begins to glow quietly at the edge of ordinary experience. Why does the world look the way it does? Why is glass transparent, coal black, gold warm and yellow, leaves green, rubies red, and the sky blue? None of these qualities are painted onto matter from outside like a finishing coat on furniture. They arise from the way light interacts with the electrons inside atoms, molecules, and solids. Colour is not a decorative extra, it is a quantum event. When light reaches a material, several things can happen. Some wavelengths may be absorbed, some may be reflected, some may pass through, some may be scattered in different directions. The result depends on the internal structure of the material and on what energies its electrons are allowed to take on. That is the crucial point. Electrons in atoms and molecules can move between specific energy levels, but only if the incoming photon carries the right amount of energy. If the energy does not match an allowed transition, the interaction will follow a different route. That is why materials do not respond to all colours of light in the same way. A pigment appears red because it absorbs many other visible wavelengths more strongly, and reflects or scatters the red part more effectively toward the eye. A leaf appears green because chlorophyll absorbs mainly red and blue wavelengths for photosynthesis, leaving more green light to be reflected. A sapphire, an emerald, a copper roof, a bright painted wall, all of them look the way they do because their electrons can and cannot respond to certain photon energies in very specific ways. This is true not only for isolated atoms and molecules, but also for solids, where the story becomes richer. In a solid, especially a crystal or metal, atoms sit close enough together that their electron states can spread into broader ranges of allowed energy called bands. Band structure is one of the key ideas in solid-state physics, and it helps explain why some materials are transparent, some are shiny, some conduct electricity, and some do not. It sounds technical, but the basic idea is quite gentle. In solids, electrons are not limited only to the isolated energy levels of single atoms. Their possible energies are shaped by the entire material. Take transparency. Glass looks clear not because it is empty, but because visible light often does not have the right energies to be strongly absorbed by the electron transitions available in the material. If photons pass through without being absorbed or scattered too much, the material appears transparent. That is why clean window glass can let the outside world arrive almost intact. The atoms are still there, the electrons are still there, but the quantum structure does not intercept visible light strongly enough to stop it. Opacity is the opposite sort of outcome. A material is opaque when incoming light is absorbed, scattered, or reflected so strongly that it cannot pass through. Wood, stone, skin, paper, and most metals do this. Their electrons respond to light in ways that prevent clean transmission. Metals in particular are interesting because some of their electrons are free to move collectively through the solid. When light hits a metal surface, those electrons respond strongly, which makes metals good reflectors. That is why polished silver or aluminium can appear so bright and mirror-like. Shininess is a quantum response with very good manners. Glow is another variation on the same story. A hot object glows because thermal energy excites matter and leads to the emission of photons across a range of wavelengths. Other materials glow through fluorescence or phosphorescence, in which absorbed photons raise electrons into higher states, and later emission returns that energy as visible light. Screens, signs, minerals under ultraviolet light, and certain deep-sea organisms all make use of this basic principle in one form or another. Even artificial color on a screen depends on electrons in carefully designed materials dropping between allowed energy states and releasing photons of chosen wavelengths. The blue sky offers a slightly different but equally revealing example. Air is mostly made of molecules far smaller than the wavelengths of visible light. When sunlight passes through the atmosphere, shorter wavelengths, especially blue light, are scattered more efficiently than longer wavelengths. This is known as Rayleigh scattering. The sky is not painted blue above the planet like a decorative ceiling. It appears blue because sunlight is being scattered by molecules in the atmosphere in a wavelength-dependent way. Even something as broad and familiar as daylight overhead is shaped by microscopic interactions. Gemstones provide another elegant case. Their colours often come from trace impurities or specific structural defects inside the crystal. A ruby owes its red colour to chromium atoms within aluminium oxide. Emerald gets its green from different impurities in a different crystal setting. Tiny changes in electron structure can transform the visible character of a mineral completely. Matter does not need much encouragement to become visually dramatic. All of this means that visual reality is not passive. Every moment of sight is built from quantum interactions between photons and matter. Light leaves a source or reflects from a surface, encounters materials that absorb some wavelengths and reflect others, passes through air, glass, water, dust, or mist, and finally reaches the eye, where molecules in the retina respond to incoming photons. Seeing is not the simple reception of a ready-made world. It is the result of an ongoing exchange between light and structured matter. So once solidity has been understood, the next step is to see how matter responds to illumination. The visible world looks the way it does because photons meet electrons that can only behave in certain allowed ways. Color, transparency, opacity, shininess, and glow all emerge from that quiet discipline. The world is visible not because light merely lands on things, but because matter answers light according to quantum rules. And in that sense, every blue sky, every pane of glass, every leaf, gemstone, screen, and painted wall is another reminder that ordinary sight rests on extraordinary physics. Heat can feel wonderfully untheoretical. A mug warms cold hands. Sunlight falls across a floor. An oven glows, a radiator hums, a candle flickers, skin gives off warmth into the surrounding air. None of this feels especially quantum at first. It feels immediate, domestic, bodily, and familiar. But beneath that familiarity sits one of the great discoveries of modern physics. Heat and light are exchanged in quantized ways, and without that fact, the ordinary thermal world would make far less sense. Any object with a temperature above absolute zero emits electromagnetic radiation. That includes stars, stovetops, walls, clouds, trees, people, and quietly cooling cups of tea. Not everything glows visibly, of course. Most everyday objects emit mainly infrared radiation, which lies beyond human sight but is very much part of the physical traffic of energy around us. Human bodies, for example, radiate strongly in the infrared. A thermal camera can reveal that invisible emission with unnerving honesty, which is one of the few times physics seems to behave like a suspiciously well-funded ghost story. This emission of radiation from warm matter is called thermal radiation. It depends on the motion and energy of charged particles inside matter, especially electrons and atomic vibrations. But the crucial point is that the exchange of energy is not continuous in the old classical sense. It occurs through quantized processes. Matter emits and absorbs radiation in discrete packets, and the allowed interactions depend on the available energy states within atoms, molecules, and solids. This is where Max Planck first changed the story. At the end of the 19th century, physicists were trying to understand the spectrum of radiation emitted by hot objects, an idealized version of which is described by blackbody radiation. A blackbody is a perfect absorber and emitter of radiation, and although it is an idealization, it captures something real about how warm objects radiate. Classical physics predicted the wrong pattern, especially at short wavelengths, where it implied an unlimited flood of high-energy radiation. Nature, politely but firmly, refused. Planck solved the problem in 1900 by proposing that energy is exchanged in discrete quanta. This was not initially presented as a grand philosophical revolution. It was a practical move to match theory to experiment. But it changed everything. Once energy was quantized, the observed blackbody spectrum made sense. The glow of heated matter from dull red metal to bright white starlight could finally be described accurately. That matters for daily life because blackbody behaviour is not some obscure laboratory curiosity. It is part of how ovens heat, how coals glow, how incandescent bulbs used to work, how skin loses energy to its surroundings, and how the sun radiates the energy that drives life at Earth's surface. A hot object does not simply leak energy in an arbitrary smear. Its emission follows patterns shaped by temperature and quantum rules. Warmer objects radiate more strongly and at shorter wavelengths on average. That is why red-hot metal can become orange, then yellow-white, as temperature rises. The colour shift reflects a changing distribution of emitted photons. The sun is the most important everyday example, even if it is easy to stop noticing that by the second or third decade of life. Sunlight is thermal radiation produced by matter at the sun's surface temperature, shaped by quantum processes inside atoms and by the broader physics of the star. Those photons travel across space and arrive at Earth carrying energy that powers weather, warms land and oceans, drives evaporation, feeds ecosystems through photosynthesis, and makes vision possible. In an ordinary practical sense, the sun is the main energy source for the surface world, and that energy reaches us through quantum-mediated radiation. This links the household and the cosmic very neatly. The same underlying principles that describe a warm loaf of bread cooling on a kitchen counter also describe starlight crossing interplanetary space. The scale changes dramatically, but the underlying logic does not. A human body radiating infrared energy, an electric heater warming a room, a star pouring visible and infrared light into space, all are expressions of matter exchanging quantized energy through electromagnetic radiation. Absorption is part of the same story. Matter does not only emit radiation, it also absorbs it, again according to its allowed energy transitions and collective behaviour. A dark surface in sunlight warms efficiently because it absorbs more incoming radiation. A lighter reflective surface absorbs less. Green leaves absorb red and blue wavelengths to power photosynthesis. Glass transmits much visible light but interacts differently with infrared. The thermal behaviour of materials, including how quickly they heat up or cool down, depends partly on these quantum-governed interactions between photons and matter. This deepens the previous discussion of colour and appearance. Colour explained why matter reflects some wavelengths and absorbs others in ways visible to the eye. Thermal radiation extends that picture into the transfer of energy itself. Light is not just what allows things to be seen. Radiation is also how energy moves into and out of matter across a huge range of wavelengths. The visible world and the thermal world are not separate. They are overlapping expressions of the same quantum framework. Even glow that seems simple often rests on a precise underlying structure. A toaster element glows because its temperature becomes high enough that part of its thermal radiation reaches visible wavelengths. Heated lava glows, filament bulbs glowed, stars glow on an incomparably larger scale, but by the same broad principle. Matter with temperature radiates. The details of that radiation make sense, only because energy exchange is quantized. So heat and light are more deeply connected than everyday intuition usually suggests. Warmth is not merely a vague feeling, and light is not merely illumination. Both are tied to the emission and absorption of photons by matter whose energy is structured in quantum terms. That is why the thermal world is not separate from the quantum world. It is one of its most constant and familiar expressions. The result is that ordinary life is saturated with quantum thermodynamics without ever announcing itself that way. The warmth of sunlight, the fading heat of a brick wall after sunset, the invisible infrared glow of skin, the bright coil of a heating element, the entire radiant economy of daily life all depend on the same underlying truth. Matter does not trade energy continuously in the old classical sense. It does so in quantized ways, and because of that the world can glow, warm, cool and shine with the extraordinary consistency that makes ordinary experience feel so natural. Electricity had been useful long before quantum physics arrived. Lamps could glow, motors could turn, telegraphs could click, and wires could carry charge from one place to another with impressive reliability. But there was a limit to how well classical physics could explain what was happening inside the materials themselves. It could describe current in a broad engineering sense, but once attention turned to the microscopic behaviour of electrons inside solids, the older picture began to lose its grip. To make electricity truly useful in the modern sense, not just present but controllable, amplifiable, switchable, and capable of carrying logic, physics needed a better understanding of how electrons move through matter. That understanding turned out to be quantum. The key point is that electrons in a solid do not behave like tiny charged beads drifting through a passive substance in the way simple intuition might suggest. In a metal, an insulator, or a semiconductor, electrons occupy a loud quantum states shaped by the collective structure of the material. The atoms in a solid site close together, and their electron states interact. Instead of remaining isolated as in single atoms, those states spread into bands of allowed energy. This is the basis of band theory, one of the most important ideas in solid-state physics. Band theory sounds forbidding, but the basic idea is manageable. In a solid, there are ranges of energy that electrons are allowed to occupy, and there are also forbidden ranges called band gaps, where no stable electron states exist. How these allowed and forbidden regions are arranged determines whether a material conducts electricity well, resists it strongly, or occupies the all-important middle ground between those extremes. Conductors, such as many metals, allow electrons to move relatively freely because they have available quantum states into which electrons can easily shift when an electric field is applied. This does not mean electrons wander about however they please, wearing tiny hard hats and taking initiative. It means the quantum structure of the metal gives them accessible states that support collective movement through the material. That is why metals carry current efficiently. Insulators are different. In an insulator, the available electron states are arranged so that electrons are not easily promoted into mobile conducting states. The band gap is too large under ordinary conditions. As a result, the material resists electrical flow. Glass, rubber, and many plastics behave this way. They are not non-electric in some mystical sense. They simply have quantum structures that do not permit easy electron movement at normal energies. Then there are semiconductors, which turned out to be the real revolution. A semiconductor has a band gap that is not too large and not too small. Under the right conditions, electrons can be encouraged to move into conducting states. Their behavior can be controlled by temperature, impurities, electric fields, or light. This is what made modern electronics possible. A semiconductor is neither a good conductor nor a strict insulator. It sits in the middle, and that middle became one of the most valuable places in technological history. Silicon is the most famous example, though germanium was also crucial in the early years. In a pure semiconductor, conduction is limited, but if the material is doped, meaning tiny amounts of carefully chosen impurities are introduced, its electrical behavior changes dramatically. Add atoms with one more outer electron than the host material, and extra mobile electrons can appear. Add atoms with one fewer, and electron absences called holes become important carriers of charge. Holes are not particles in the same sense as electrons, but they behave as useful positive charge carriers in the material. This is one of those moments where physics seems to reward patience with a concept that initially sounds fake, and then turns out to run half the modern world. This controlled behavior of electrons and holes allowed physicists and engineers to create junctions between differently doped semiconductor regions. Those junctions made it possible to direct current preferentially, to switch it, and eventually to amplify signals. That was the foundation of the transistor, the device that transformed electronics from bulky, fragile, power-hungry vacuum tube systems into compact, reliable, scalable technology. The transistor emerged most famously at Bell Labs in the United States in the late 1940s. Bell Labs had become a remarkable center for applied and theoretical research, bringing together physics, engineering, and material science. In 1947, John Bardeen, Walter Brattain, and William Shockley were central figures in the creation of the first practical transistor devices. Their work depended not on vague electrical cleverness alone, but on quantum understanding of how semiconductors behave. Without band theory, without the quantum description of electron states in solids, the transistor would not have appeared when it did, and perhaps not in anything like the same form. The transistor matters because it made electricity useful in a new way. Electricity was no longer just something that could heat a filament or spin a motor. It became something that could represent information, perform logic, amplify voices, store memory, and coordinate machines. One transistor can act as a switch. Millions or billions of them can build integrated circuits. Integrated circuits became microprocessors, memory chips, and communication systems. From there came modern computing, digital networks, mobile phones, satellite systems, and a great many glowing rectangles that now command human attention with more authority than most monarchs ever managed. This is why the quantum story becomes fully tangible here. The modern everyday world depends on making quantum behavior technologically usable. Lighting systems, radio transmission, medical devices, computers, internet infrastructure, digital cameras, and communication networks all rely on materials whose electron behavior only makes sense through quantum theory. Even something as routine as typing a message or checking the time on a phone depends on billions of controlled quantum events inside semiconductors working together at astonishing speed. This development also connects naturally to the earlier discussion of heat and radiation. There, the focus was on the general exchange of energy between matter and light. Here, the focus narrows to the controlled movement of electrons through materials. In both cases, the key is that matter does not behave classically at small scales. Allowed states, band structure, and quantized behavior shape the outcome. The difference is that in electronic materials, those quantum rules are not just observed, they are engineered. That may be the most remarkable part. Human beings did not invent quantum behavior, but they learned to build with it. They learned how to choose materials, add impurities, shape junctions, and design circuits so that the microscopic laws of electron states could be turned into switches, signals, and systems. Modern civilization runs on that achievement. Electricity became truly useful in the deepest modern sense when quantum physics explained how to guide electrons through matter without guessing. So the path from atomic structure to everyday technology is not as long as it first appears. Once electrons were understood as quantum objects in solids, conductors, insulators, and semiconductors stopped being mere categories and became ways of organizing behavior. Band theory revealed why materials differ. Solid-state physics turned that understanding into design. Bell Labs and the transistor made it practical, and from that came the electrically powered, electronically mediated world that now feels ordinary, which is another way of saying that ordinary life has once again been built on quantum foundations, only this time with a power cord attached. By the time quantum physics reaches the level of everyday devices, it has already stopped being an abstract theory about strange particles and become something much more intimate. It is in the phone screen lighting a dark room, in the chip processing a search, in the camera collecting an image, in the timing signals guiding satellite navigation, and in the hospital scanner producing pictures from inside the body. Quantum theory is not sitting off to one side of modern life as a specialist curiosity. It is built directly into the tools that now shape ordinary routines so completely that many of them feel less like inventions and more like weather. The transistor remains the central example because it made modern electronics possible. A transistor controls electrical current through semiconductor materials whose behaviour depends on band structure and carefully engineered electron states. Pack enough transistors into a tiny chip, and they can perform logic, store memory, and process information at extraordinary speed. Computer chips are therefore not just feats of miniaturization. They are dense arrangements of quantum-controlled switches. A modern processor may contain billions of transistors, each relying on the behavior of electrons in materials such as silicon. The fact that this works reliably is one of the great triumphs of solid-state physics and engineering, and one that Bell Labs helped set in motion. Lasers are another beautifully direct expression of quantum theory. The word stands for light amplification by stimulated emission of radiation, though thankfully most people do not have to say that every time they scan a barcode. A laser works because atoms or other quantum systems have discrete energy levels. When electrons in those systems are excited and then encouraged to drop in a coordinated way, they emit photons of the same energy and phase. That process is called stimulated emission. The result is a highly focused, coherent beam of light. Lasers now appear in fiber optic communication, barcode scanners, surgery, manufacturing, research instruments, and everyday electronics. A theory once accused of being too strange to represent reality now helps supermarkets function with admirable efficiency. Light-emitting diodes, or LEDs, rely on related principles. In a semiconductor LED, electrons and holes recombine across an energy gap and emit photons. The energy difference determines the color of the light. That means the glow of an indicator lamp, a television display, or a city street light can be traced back to discrete energy transitions in engineered materials. Modern lighting, with its efficiency and compactness, depends heavily on this quantum control of emission. Solar cells reverse the story in a useful way. Instead of using electricity to make light, they use light to make electricity. Incoming photons strike a semiconductor and can promote electrons into mobile states, creating charge carriers that can be separated and directed into a current. This is another case where band structure matters deeply. A solar cell works because the quantum behavior of electrons in a semiconductor can be harnessed to convert sunlight into usable electrical power. The sunlight falling on a roof is ancient stellar radiation. The panel receiving it is modern quantum engineering. Between them sits a surprisingly elegant conversation. Digital cameras also depend on quantum ideas. In a camera sensor, incoming photons strike semiconductor materials and free electrons, producing signals that can be measured and turned into an image. In that sense, photography in the digital age is an organized counting of light. A camera does not merely open an eye onto the world. It registers photon interactions in carefully designed arrays. Every image on a phone or tablet is built from quantum events translated into electronics. Magnetic resonance imaging, often called MRI, reaches into a different part of quantum physics. It depends on spin, a quantum property of particles such as protons. In a strong magnetic field, those spins can align in particular ways. Radio frequency pulses can disturb that alignment, and as the system relaxes, measurable signals are produced. From those signals, detailed images of tissues inside the body can be reconstructed. This is one of the most quietly astonishing uses of quantum theory in daily civilization. A patient lies inside a scanner, and a machine built on quantum spin properties helps produce a medical image detailed enough to guide diagnosis and treatment. Atomic clocks may be even more quietly influential. They keep time by using highly regular transitions between energy levels in atoms, often cesium or other carefully chosen species. Because those transitions are extremely stable, They provide precise standards of time. National metrology laboratories and standards bodies rely on atomic clocks to define and maintain timekeeping used across communication networks, financial systems, scientific measurements, and satellite navigation. When a phone finds its position through global navigation systems, that accuracy depends on exquisitely precise timing. In practical terms, knowing where you are on a map depends on measuring atomic behaviour with absurd care. Institutions such as Bell Labs were crucial in turning quantum ideas into technology. CERN is better known for probing fundamental particles than for household gadgets, but it represents the same broader truth. Modern civilization depends on taking quantum theory seriously enough to build with it, test it, and trust it. National laboratories, standards, institutes, semiconductor research centres, hospitals, and communications industries all make use of principles that once seemed bizarre even to many physicists. That is what makes this so important. Quantum physics is not only a theory of the tiny, it is a working foundation for the devices that structure modern daily life. Checking a phone, sending a message, using the internet, navigating by satellite, switching on an efficient light, scanning a code, taking a photograph, or receiving medical imaging all depend on ideas that began as uncomfortable revisions to classical certainty. So the controlled electrical behaviour of matter did not merely improve a few machines, it became the basis for an entire technological civilization. Quantum theory moved from atoms and spectra into chips, beams, clocks, sensors, scanners, and networks. The strange behaviour of electrons, photons, and spins became not just understandable, but practical. And once that happened, the quantum world stopped hiding only beneath reality and began sitting openly on desks, in pockets, on walls, above roads, and beside hospital beds, quietly running the routines of modern life. After following quantum physics through atoms, solids, and devices, it is worth returning to a quieter and more intimate fact. The same laws also operate inside living things. Biology can feel different from physics because it is full of cells, tissues, organs, ecosystems, and evolution, all layered with history and complexity. But living matter is still matter. A body is built from atoms. Cells are built from molecules. Molecules are held together by electron interactions, and those electrons obey quantum mechanics whether they are inside a computer chip or inside a leaf. This is not a claim that biology is mystical or secretly magical. Quite the opposite. It is a reminder that life became possible because the same microscopic laws that govern non-living matter also govern living chemistry. The difference is not that life escapes physics. The difference is that life organizes physics into systems that persist, regulate themselves, and reproduce. Every chemical reaction inside a cell depends on quantum principles. Bonds form and break because electrons can occupy some states and not others. Enzymes work by lowering energy barriers and guiding molecules into favorable arrangements. But the actual making and breaking of bonds is still a quantum story. Metabolism, respiration, digestion, signaling and growth all rely on electrons being transferred, shared, or rearranged in specific ways. A living cell is not a sack of vague biological intention. It is a crowded quantum chemistry laboratory that somehow runs continuously without demanding applause. DNA is another clear example. Its structure depends on chemical bonds, electron distributions, and the shapes of molecules. The famous double helix holds together because of covalent bonds along its backbone and weaker interactions, including hydrogen bonding, between complementary bases. Its ability to store information in a stable yet readable form depends on the molecular architecture permitted by quantum-governed chemistry. Proteins are similar. Their amino acids bond into chains, fold into specific shapes, and carry out functions because of how electrons shape attraction, repulsion, charge distribution, and molecular geometry. The body's structure and activity rest on this invisible order. Erwin Schrödinger recognized the importance of this bridge between physics and life in his book What is Life, published in the 1940s. He was not offering a complete biological theory, and much of modern molecular biology would develop afterward, but he helped encourage the idea that life should be understood as physically lawful rather than exempt from basic science. That was an important shift. It helps frame the living world not as a special exception to matter, but as one of its most intricate consequences. There are also more direct encounters between biology and quantum events. Vision is one of the most striking. In the retina, light-sensitive molecules respond to incoming photons. Under the right conditions, even a single photon can trigger a molecular change that begins the cascade leading to visual perception. That means one of the most intimate forms of experience seeing can begin with an individual quantum event. Conscious awareness is still a biological and neurological process on a much larger scale, but its opening move can be a photon meeting a molecule in the dark. Photosynthesis offers another beautiful case. Plants, algae, and certain bacteria capture light using pigments such as chlorophyll. Photons are absorbed, electrons are excited, and that energy is channeled into chemical processes that ultimately store energy in molecular form. The food web, the oxygen content of the atmosphere, and much of the surface biosphere depend on this conversion of light into chemistry. Once again, quantum interactions are not sitting politely in the background. They are doing the work. So the same theory that powers transistors, lasers, and digital cameras also underlies metabolism, sensation, and the chemistry of living tissues. The difference is mostly one of organization and scale. In technology, quantum behavior is engineered. In biology, it is evolved and regulated. But in both cases, the underlying laws are the same. Living matter does not stand outside the physical world. It is one of the most elaborate things the physical world has managed to build. That makes the ordinary body a rather remarkable place. Warm skin, beating muscle, signaling nerves, folding proteins, replicating cells, and light-sensitive eyes all depend on atoms and electrons obeying quantum rules with extraordinary consistency. Life feels rich, continuous, and immediate. Underneath, it is still built from the same quantum foundations as everything else. By this point, a fair question begins to hover over everything. If quantum mechanics is so fundamental, why does the ordinary world not look more obviously quantum? Why do tables stay put, clouds drift in recognizable ways, buildings remain reassuringly building-shaped, and human beings do not usually spread themselves across a room like uncertain probability clouds? If the underlying rules are so strange, why does everyday life seem so calm, so definite, and so stubbornly classical? The short answer is not that the large world escapes quantum physics. It is that the large world is what quantum physics looks like when enormous numbers of particles interact constantly with one another and with their surroundings. The familiar world is not separate from the quantum world. It is an emergent version of it, a large-scale appearance that arises when the delicate features of microscopic quantum states are rapidly suppressed. One of the most important ideas here is decoherence. Decoherence is the process by which a quantum system loses the kind of coherent behavior that makes superposition and interference visible. A small, carefully isolated quantum system can preserve subtle relationships between possible states. That is when wave-like combinations and interference effects can be observed clearly. But large objects are not isolated. They are constantly interacting with air molecules, photons, thermal vibrations, nearby surfaces, internal motion, and everything else in their environment. Those interactions entangle the system with its surroundings and rapidly destroy the fragile coherence needed for distinctly quantum behaviour to remain visible. That is why a single electron can show interference in an experiment, while a chair does not appear in two places at once in any useful everyday sense. The chair is made of an enormous number of particles. More importantly, it is also embedded in a busy environment that is constantly interacting with it. The quantum possibilities do not vanish in some magical way, but the clean, delicate patterns that would reveal those possibilities become scrambled into the wider world extremely quickly. Decoherence makes certain outcomes effectively stable and classical looking. A good way to think about it is that the environment is constantly monitoring large systems whether anyone asked it to or not. Light scatters off surfaces, air molecules collide with them, heat flows in and out, internal vibrations ripple through matter. All of this means that large objects are never isolated enough to preserve the kind of pristine quantum behaviour that laboratory systems can sometimes display. The world is not hiding quantum mechanics out of shyness, it is overwhelming it with interaction. This is one reason classical physics works so well for everyday objects. Classical descriptions are not fundamentally separate laws governing a different universe. They are highly effective approximations that emerge when quantum systems become large, complex, and environmentally entangled. A football follows a trajectory that can be described classically because the quantum features that would matter for an electron are utterly negligible at that scale. A planet orbits a star without obvious superposition, effects, not because quantum mechanics has stopped applying, but because the classical description becomes extraordinarily accurate for that situation. This understanding was sharpened by modern work on decoherence, especially by physicists such as Wojciech Zurek. His contributions helped clarify how classical-looking behaviour can emerge from quantum systems through interaction with the environment. The key insight is that the world does not need a second separate set of rules to explain why tables seem definite. Quantum systems interacting with their surroundings naturally tend to produce stable, robust states that persist and can be observed repeatedly. In effect, the environment favours certain kinds of behaviour over others, and those are the ones that come to define the macroscopic world of common experience. That means classical reality is not an illusion in the cheap sense, and it is not wrong. It is real as an emergent level of description. A table is still a table, a body is still a body, a cloud is still a cloud. But all of them are quantum built. Their atoms obey quantum mechanics. Their stability depends on quantum states, exclusion principles, chemical bonds, and electron behaviour. It is just that, once scaled upward through vast numbers of interactions, the result looks definite and well-behaved enough that simpler classical rules often do the job perfectly well. This also explains why the quantum-built world usually hides its own foundations. Technology and biology gave many examples of quantum rules doing important work. But the reason those examples sometimes feel surprising is that most of the time, the underlying machinery stays out of sight. Floors feel solid, leaves look green, bodies remain coherent, and buildings do not dissolve into visible uncertainty, because decoherence and large-scale organization keep the world looking stable. So the large world appears non-quantum, not because it is built on something different, but because quantum behavior changes its appearance when repeated across immense numbers of particles in constant contact with the environment. Tables, clouds, bodies, and buildings are still made from quantum matter. Their classical look is not a rejection of quantum physics, it is one of its most successful, large-scale outcomes. In that sense, the ordinary world is not less quantum than the microscopic one. It is simply what quantum reality becomes when it has had time, scale, and countless interactions to settle into something that feels almost reassuringly normal. If the large world looks stable, because quantum behaviour is usually hidden beneath scale and constant interaction, the next question is harder to avoid. What is the quantum world actually saying about reality underneath? Because quantum mechanics does not describe nature in the old classical way, with tiny objects moving along neat, fully determined paths whether anyone looks or not. Instead, it describes allowed states, probabilities, and measurement outcomes. That shift is one of the deepest changes in the history of science. In classical physics, the ideal was clear. If the position and motion of something were known exactly, then its future could in principle be calculated. A planet would follow its orbit, a stone would trace its arc, and the universe would unfold like an elaborate but obedient machine. Quantum mechanics replaced that picture at small scales with something less comfortable, but far more successful. It does not generally tell us that a particle has one exact path hidden neatly behind the scenes. It tells us what states are allowed, how those states evolve, and what probabilities are associated with different outcomes when a measurement is made. That does not mean quantum theory is vague or imprecise. In fact, it is one of the most accurate scientific theories ever developed. Its predictions have been confirmed to astonishing precision in experiment after experiment. The oddness lies not in weakness, but in what kind of description it provides. It gives extremely reliable probabilities rather than the sort of exact microscopic storyline classical intuition hoped for. This is where the measurement problem enters. In broad terms, the measurement problem asks how a quantum system described by a spread of possible outcomes becomes the single definite result actually observed. Before measurement, the formalism allows combinations of possibilities. After measurement, one specific outcome appears, explaining that transition has been one of the most discussed conceptual questions in quantum theory. It is important not to make this sound more mystical than it needs to be. The problem is not that physics collapses into nonsense the moment anyone opens their eyes. The issue is that the mathematical description of quantum systems and the definite character of observed outcomes do not line up in the straightforward classical way people once expected. Quantum mechanics works brilliantly, but it changed what counts as a satisfactory physical description. Instead of always asking, what is the particle really doing at every instant, the theory often asks, what outcomes are allowed, and with what probabilities. Different interpretations try to make sense of this. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, treats the quantum description in terms of measurement outcomes and observable quantities, rather than insisting on hidden classical pictures underneath. On that view, the demand for a fully classical account of what happens between measurements may simply be the wrong demand. The many worlds interpretation, proposed later by Hugh Everett, takes a different route and suggests that all possible outcomes remain part of a larger branching quantum reality, even though any observer experiences only one branch. There are other interpretations too, but the key point is not to settle the argument here. It is to notice that the meaning of quantum theory remains philosophically rich, even while its practical predictions remain extraordinarily successful. That matters because this entire journey has been about how quantum physics built everyday reality. The visible world of stable objects, colours, chemistry, devices, and living bodies was produced by rules that are not especially intuitive when examined closely. Everyday life feels definite, local and solid. The rules underneath describe probabilities, allowed states, superpositions and outcomes shaped by measurement and interaction. The calm familiarity of ordinary experience rests on a deeper layer that does not mirror ordinary common sense. This is not meant to make the world feel unreal. Quite the opposite. The point is that reality is more structured and in some ways stranger than intuition alone would suggest. Common sense is useful because it was shaped by large objects moving slowly through everyday conditions. It was not designed for electrons, photons, or atomic states. So when quantum mechanics feels conceptually awkward, that is not necessarily a sign that something has gone wrong. It may simply be a sign that human intuition was trained in the wrong part of the universe for this particular job. And yet the results of those unfamiliar rules are all around us. Stable atoms, chemical bonds, solid matter, visible color, flowing electricity, digital devices and living tissues all emerge from a framework that does not describe the world in terms of miniature billiard balls following tidy tracks. That is the real significance of probability, measurement and interpretation. They remind us that the world people live inside was built by principles that are fundamentally less intuitive than the world they produce. So the purpose here is not to leave everything in fog. It is to recognize a boundary. At large scales, the world becomes definite enough to feel ordinary. Underneath, quantum mechanics gives a different kind of description, one based on possibilities, constraints, and measured outcomes rather than classical certainty. The stability of daily life depends on that deeper layer, even though it does not resemble daily life very closely when viewed on its own terms. In that sense, the quantum world hides twice. It hides practically, because large systems decohere and look classical. And it hides conceptually, because the rules beneath familiar reality do not align neatly with intuition. But they are the rules that built the world anyway. By now, the ordinary world looks a little less ordinary. A table is no longer just a table. A pane of glass is no longer just a pane of glass. Sunlight on a wall, the colour of a leaf, the warmth of skin, the function of a phone, the chemistry of a cell, all of it begins to look like the visible surface of something deeper. Not a second hidden universe tucked behind the first one, but the same universe understood more fully. Everyday reality is not merely compatible with quantum mechanics, it is continuously produced by it. That is the central shift. The world once seemed explainable as a machine built from tiny hard pieces moving along clear paths. That picture was powerful, and for large objects it still works remarkably well. But it turned out not to be fundamental enough. Matter is not built from little classical pellets with simple trajectories. Light is not just a wave or just a particle. Atoms are not miniature solar systems. Underneath familiar experience lies a layered world of quantum states, fields, probabilities, standing wave patterns, exclusion rules, and structured interactions. The world is not less real for that. It is more intricate than it first appears. It began with the breakdown of classical certainty. Max Planck, trying to solve the problem of black-body radiation, found that energy had to be exchanged in discrete quanta. Albert Einstein then showed that light itself behaves in quantized packets in the photoelectric effect. That alone would have been enough to make the foundations of physics uncomfortable. But the discomfort spread. Atoms became physically real through chemistry, spectroscopy, Brownian motion, and the work of people such as John Dalton, Albert Einstein, John Perrer, and Dmitri Mendeleev. Then light turned out to behave like both a wave and a particle. Then matter did the same. Once Louis de Broglie proposed that matter has a wavelength, and experiments by Clinton Davison, Lester Germer, and George Paget Thomson confirmed electron diffraction. The old picture of matter as tiny billiard balls could no longer survive in peace. Electrons had to be treated as quantum objects. That changed the atom from a simple mechanical image into a structured quantum system. Niels Bohr gave an early model with quantized energy levels. Werner Heisenberg showed that uncertainty is built into nature itself, not merely into instruments. Erwin Schrödinger provided wave mechanics and a way to calculate atomic states. Wolfgang Pauli added the exclusion principle, which quietly became one of the great architectural rules of matter. From there, the visible world began to assemble itself piece by piece. Stable atoms exist because electrons occupy allowed states rather than collapsing into the nucleus. Orbitals replaced little planetary tracks and revealed pattern distributions of probability. Those patterns explained the periodic table, the identity of elements, and the diversity of chemistry. Bonds formed not because atoms had tiny hooks and admirable teamwork, but because electron arrangements could settle into lower energy configurations. Ionic, covalent, and metallic bonding built salts, water, minerals, metals, proteins, plastics, and the chemical framework of both geology and biology. Then the story widened further. Matter feels solid not because atoms are dense little stones, but because electromagnetic interactions and the Pauli exclusion principle prevent unrestricted overlap. Color appears because electrons in matter absorb and reflect specific photon energies. Transparency, opacity, shininess, and glow all depend on how light interacts with atomic and solid-state structure. Heat and thermal radiation make sense because energy is emitted and absorbed in quantized ways. The sun itself, that suspiciously overachieving ball of plasma in the sky, powers weather, ecosystems, and vision through quantum-mediated radiation reaching Earth across space. Electricity became truly transformative once the quantum behaviour of electrons in solids could be controlled. Band theory explained the difference between conductors, insulators, and semiconductors. Solid-state physics revealed why silicon and other materials could be engineered to guide charge in useful ways. At Bell Labs, John Bardeen, Walter Brettin, and William Shockley helped turn that understanding into the transistor. From there came computer chips, digital logic, communication systems, and the technological civilization now wrapped around daily life so thoroughly that most people encounter quantum mechanics before breakfast without calling it that. The same theory also built the tools of modern routine. Lasers rely on stimulated emission between discrete energy levels. Light-emitting diodes produce photons through controlled semiconductor transitions. Solar cells convert sunlight into electrical current by promoting electrons into conducting states. Digital cameras count light through photon-sensitive semiconductor arrays. Magnetic resonance imaging depends on quantum spin. Atomic clocks use highly stable atomic transitions to keep time with extraordinary precision. So the strange rules once introduced to explain awkward laboratory results now guide navigation, communication, imaging, lighting, and information processing across the planet. And then the story came home again, because living things were never outside it. Cells, proteins, DNA, vision, and photosynthesis all depend on atoms, molecules, and electron interactions governed by the same quantum laws. Schrödinger's "What is life?" helped encourage the recognition that life should be understood as lawful matter rather than a special exception. Biology is not mystical physics, it is organized chemistry, and chemistry is quantum structure doing long, patient work. Still, the everyday world does not look especially quantum most of the time. Tables stay in place. clouds drift without visible interference patterns, people do not usually arrive at breakfast in superposition. Decoherence helps explain why. Large systems interact constantly with their environments, and those interactions suppress the delicate coherence that makes quantum effects obvious at small scales. Classical reality is not separate from quantum reality. It is the large-scale appearance that emerges when quantum systems become complex, warm, entangled, and relentlessly interactive. Wojciech Zurek and others helped show how that classical-looking world can arise naturally from the underlying theory. Even so, the deeper layer remains strange. Quantum mechanics describes probabilities, allowed states, and measurement outcomes rather than neat deterministic paths. The Copenhagen interpretation and the many worlds interpretation differ in how they frame what that means, but both remind us that the conceptual meaning of the theory remains richer and more unsettling than the smooth surfaces of daily life would suggest. The most familiar things in existence rest on principles that are mathematically powerful, experimentally verified, and still philosophically difficult. So when the world is reconsidered after all this, it does not become less familiar, it becomes more complete. A flaw is still a flaw, a leaf is still a leaf, a body is still a body. But each one is now visible as the large-scale expression of quantum-built structure. Atoms, light, chemistry, solidity, electricity, devices, living tissue, and emergence are not separate stories. They are parts of one story. The ordinary world is the visible consequence of invisible rules, repeated with astonishing consistency across immense scales. And that may be the quiet wonder at the heart of it all. The most familiar objects in daily life are not simple, they are successful. They are what quantum reality looks like when it has built enough structure to become wood, skin, glass, water, circuitry, breath, and sight. Everyday reality was not placed gently on top of the quantum world. It was made from it, and it is still being made from it now. The world rarely introduces itself as a quantum construction. It arrives instead as touch, colour, warmth, pressure, breath, wood grain, glass, rain, skin, sunlight, and the low electric glow of familiar devices. It feels immediate and stable. It feels ordinary, and that is precisely why its deeper structure can remain hidden so easily. The quantum foundations of reality do not hide because they are rare or remote. They hide because they are woven into everything so completely that the finished surface feels natural. That surface is built from quantized energy, atomic structure, electron behaviour, and the emergence of large-scale order from microscopic rules. That was the central promise all along. Everyday reality was not merely influenced by quantum physics at a distance, it was built from it. The ordinary world exists in the form it does because energy comes in quanta, because atoms have stable internal structure, because electrons occupy allowed states, because matter forms bonds, because light interacts with these bonds in specific ways, and because vast collections of microscopic events can produce a world that feels calm, continuous, and definite. The path to that understanding began when classical physics, for all its beauty and power, started to fail. It could explain planets, pendulums, and projectiles, but not the behaviour of radiation, atoms, and very small systems. Max Planck's work on blackbody radiation opened the first crack by showing that energy had to be treated as discrete. Albert Einstein extended the strangeness by showing that light itself behaves in quantized packets. Matter then followed. Atoms became real through chemistry and experiment. Electrons revealed wave-like behavior. The atom had to be rebuilt as a quantum system, rather than imagined as a tiny solar system that should, by classical logic, destroy itself. From there, structure emerged. Quantized energy levels explained atomic stability and emission spectra. Orbitals replaced tidy orbits with patterned probability. Wolfgang Pauli's exclusion principle gave matter layering and resistance. Chemistry arose from electron behaviour, shared states, and energy minimization. Ionic, covalent, and metallic bonding built the substances of the world. Solidity came not from tiny hard stones packed together, but from electromagnetic interactions and quantum exclusion. Colour, transparency, and glow emerge from how electrons in matter absorb, reflect, and emit photons. Heat and light became part of the same story, linked by thermal radiation and quantized exchange. Then the same principles moved outward into civilization. The controlled behaviour of electrons in solids gave rise to conductors, insulators, and semiconductors. Band theory made sense of materials. The transistor made quantum behaviour useful. Electronics, computing, communication, timing, imaging, and countless ordinary technologies became possible because quantum rules could be engineered rather than merely observed. And even after all of that, the story still returned to living things, because cells, proteins, DNA, photosynthesis, and vision all depend on the same atomic and electronic principles. Life did not escape the quantum world. It learned to live within it. That is perhaps the most quietly beautiful outcome of all this. The ordinary world is not less real because its foundations are strange. A table is still solid, a leaf is still green, a body is still warm, a clock still keeps time, a window still lets in morning light. Quantum physics does not dissolve the reality of those things. It deepens it. It shows that familiarity is not the absence of mystery. Familiarity is often mystery repeated so consistently that it begins to feel obvious. So the next time light falls across a wall, or a hand rests on a table, or a breath leaves warm air in a cold room, or a screen wakes in the dark, there is another way to see it. Not as separate phenomena scattered through life, but as expressions of the same hidden order. The colours, the surfaces, the warmth, the chemistry, the signals, the living tissues, all of them arise from a world built on quantum rules so old, so constant, and so deeply embedded that they disappear into the background of experience. And perhaps that is the most fitting place to end. The world around you is not simply made of things. It is made of patterns, states, interactions, and structures that begin far below sight and rise patiently into ordinary life. The next surface, the next colour, the next breath, the next beam of light, the next quiet device in your hand will be another reminder of the same truth. Everyday reality is not standing above the quantum world. It is the quantum world, arranged so beautifully and so reliably that it feels, most of the time, like home.